Pushpita and pleased to that I actually that I actually sequenced PhD program. Uh, I am the TA for the course Applied Optics. So today is the extra class. So last day I have discussed some actual application of optics like anti-reflection coating and fiber, then holography, then laser, and all those things. So today I want to show you some cross section of fiber. See, this is a cross section of fiber. So actually, this fiber contains actually this wire contains two fiber, core and cladding, and like this thing contains two fibers, and this is the core strength material, and another things are like like they are packed sheathing material, and and six fiber, the cross section are this white portion contains six uh, optical fiber. So as I have said that to couple wave in those tiny a little bit position is actually we need to know which angle at which angle we need to couple those lights. So without a further ado, I'm gonna start today's extra something I want to discuss. So last day we discussed laser, like like show you uh, just one question that is basically the population to energy levels and kind of thing. So today, okay, I'll describe something. So an example. So we see uh, A to 1 by A to 1. You need is almost equal to one by 2. It's basically H CQ. So in the visible range with ordinary optical sources, Each new is physical. So, on the emission or as an example, for T 10 to the power 3 Kelvin, mu, which is in 14 second universe within the 6,000. So, it is by K to those times again is 5 times of 14 second universe. K plus 10,000 is 1 and for the last 22 Kelvin universe. 10 to the power 3 Kelvin time. This is 24. So A to 1 by B to 1 is e to the power 24 minus 1, which is 10 to the power 10. So you see, that's empty. So transition. So when it's new, it's greater than 80. But when H new is less than 80, for example, lambda 10 centimeter. So assuming mu to be 3 into 10 to the power 6, and room temperature is room. This happened like it should basically 5 into 10 to the power 9. So like B2 UB is equal to 85 K minus 5 into 10 minus 4 minus 5 into 10 minus 4. So here A21 is 5 into 10 to the power minus 4 times BT, and B21 is limited addition. So for H greater than K, is like spontaneous emission is emission is so we have seen that during the particle there is a medium. Clearly the light structure is better. So this is actually the length, this is length of every optical rays of light. So the length is L, which we are 2 pi lambda into L is to m pi. It can be 1, 2, 3. So basically, I will start traveling from one mirror, then towards the other. It it passes through and so the second mirror is partially 100% reflected and then 99% reflected. So this is partially reflecting, or is partially and it's just reflect back toward the first mirror. In traveling to the first mirror, the wave is again amplified and returns to the final position. So thus in between the two positions, there is propagating on both directions. So the waves travel L plus L plus distance. And in this round, their like distance should be like start from that way, then travel black that way. So cover distance of in one round trip. Basically, on round is suffered should be multiple of 2 power. That's why this equation comes. So the mu is lambda or lambda. So we get C. So this mu is 1, 2, 3. They are discrete modes. So which gives discrete equation oscillation. Distance between these two equations is C. And C is moving to L C. So for optical resonance, we can see that M is very large. This assume for L, so and mu it is F5 into 10 to the power 40 Hertz. This corresponds to 6,000 angstrom. M is mu into that is 2 to the power 6. So we can take moves of frequency. And if cannot for diffraction is lambda by A is A. is maybe as a dimension of 1 centimeter. Then wavelength of so here remember put L is there once I did it in 16 10 to the ones to 6,000 10 to the power minus 10. So this is equal to 330. This is greater than 1. Then the deflection loss is so discussion is also wrong. But it also to just briefly describe what are different kind of like whether there some of these systems. So there is ruby laser. Uh, for the ruby laser emission is at 6943. And the YDA laser. So I can describe ruby laser a little bit. So this is E1, this is E2, this is E1, this is E3. This meta cell is this is shortly. So there are questions in the NET exam that which state is short-lived, which state is long-lived, which transition rest it's quick. So you need to like for the something happens 15, 55 minutes, and this is basically the active medium here is the reward, and the Ruby laser was the first laser. This is a very first laser, 1960. The round is the active medium. And Ruby laser is pulsed laser. And in YAG laser is a full solid state laser. So here various energy levels of ND neon atoms are produced. So here like portable laser, this is and here is so we've done this this has a 10.5 degrees. So as duration here is about 0.1 second. This is also duration is almost here on laser. So the laser here. So the pumping here for the mine. Obviously, yeah, so what can happen from there it's 18.70 electron volt. Then there is a state where this is basically spontaneous transition, and this is radiation-less transition. So basically, when a discharge, you need to remember that this is a gas laser. So what happened when when an excited a discharge is passed through the gas mixture, electrons are accelerated down the tube. These accelerated electrons and pump the helium atoms and also the neon atoms to metastable state, 20.61 electron volt and 20.66 electron volt respectively above their ground state. And some of these excited helium atom transform their energy to ground state neon atoms by collision. So when an excited neon atom passes spontaneously from the metastable state at 20.66 electron volt to the state of 18.70 electron volt, it emits a 6,328 angstrom photon. This photon travels through the gas mixture and it is moving parallel to the axis of the tube. It's reflected back and forth by the mirror ends until it stimulates an excited neon atom and causes it to emit a fresh uh, 6,328 angstrom photon in phase with the stimulated photon. This stimulated transition from 20.66 electron volt to 18.70 electron volt is the laser transition. And this is a tunable laser. Then you can go to carbon dioxide laser. So it is a molecular gas. Carbon dioxide bends. There are symmetric stretching, bending modes, and asymmetric stretching modes. So these modes have different energy levels. So here, carbon dioxide and nitrogen gas mixture is used. And the lasing action give us 10.6 micrometer wavelength and 9.6 micrometer wavelength. Nowadays, there are many semiconductor injection laser, then where p-type and n-type semiconductor is used as an active medium. There are also tunable lasers. And there is dye lasers. These are actually liquid laser which have several advantages over solid state laser. Organic dye dissolved in a suitable solvent like ethyl alcohol, methyl, or benzene, water is used as an active medium. This is the active medium. And there is dye laser. So here the organic active medium is dye mixed with or dissolved in, sorry, mixed and dissolved are two different things. Suitable solvent like ethyl alcohol, methanol, benzene, toluene, water, etc. More details you can find in Laser Book by A. Khatak, Ajay Khatak, and K. Thiagarajan. And also in Atomic and Molecular Physics book by Rajkumar. So, in a roundup, in this course, we have gone through various topics. So, since you are going to appear in an exam, so they are geometric optic, there is Fermat principle, refraction formulas, diagram, lens related questions, matrix method, paraxial optics assumption, thick lens and thin lens formula, gone through interference. In interference, we have seen Young's double slit, division of amplitude, division of wavefront, multiple beam interference, peripheral interferometer, also discuss the theory of coherence. We have gone through diffraction, Fraunhofer diffraction, this diffraction, their condition, half period zone, vibration cards, discuss single slit, double slit, grating, circular aperture, rectangular aperture, period zone, vibration curve. Then we came to the polarization. There we have discussed quarter of plate, half wave plate, then light circular polarization, left circular polarization, right elliptical polarization, plane polarization. Left elliptical polarization, we got to know that plane polarization, right circular polarization is a special case of plane polarization, and right circular polarization and left circular polarization. Special case is elliptical polarization. Then E ray, O ray, birefringence, Malu's law, Brewster angle, and then the last week we have gone through anti-reflecting coating, holography, how holography is recorded and reconstructed, optical fiber, laser. So I have discussed the theory in the tutorial once again uh, because of better understanding and also problems. So basic theory of all topics and problems, simple problems. That would be enough. So when we are talking about simple topics, especially in the laser, you should know that which wavelength is being generated by which laser. That is very important. Mm. So I could not discuss some question in the half period zone time. So just I want to give some simple formula. So for the half period zone, radius the radius is b into lambda. So b is basically, if these are half period zones, uh, b is the distance from the point, and this is b plus lambda by 2, b plus lambda, so on so forth. So from this you can solve questions. If r is increased, then how the intensity is increased, and so on and so forth. So, and the radius of the emeth first half period zone, and for emeth half period zone, outer radius is almost mb lambda, and inner radius is m minus 1, which is the outer radius of minus m minus 1 and half period is that. So let's any example. Calculate the outer and inner radii of the 10th half period zone for plane wave front with respect to a point at a distance point 5 meter from it. Assume lambda is 500 nanometer. So our 10th would be 10 into 0.5 meter into 500 into 10 to the power minus 9. And that would be 1.58 millimeter. R9, which is the inner radius of 10th zone, is basically 9 into 0.5 meter into 500, 10 to the power minus 9. So similarly, the inner radius of 11th half period zone would be outer radius of 10th half period zone, and that becomes 1.5 millimeter. So that's for today and for the class. All the best for the exam. Thank you.